So do it like that. Thank you very much for coming. I'd like to talk about the data center, the network in the data center, and why I feel the data center is particularly ripe territory for OpenFlow to make a real difference. Taking a step back and looking at this problem from the point of view of historical evolution, if you think about where layer 2, layer 3 networks came from, you've got to rewind your brain back to late 70s, early 80s, maybe mid 80s, and think about what networks in various organizations like universities looked like then. And networking grew up as little islands of connectivity, departmental LAN here, departmental LAN there, people doing email, little groupware sorts of things, remote printing, file servers were like a new concept. And in this environment, people started wanting to interconnect these networks together. These were networks run by different people in different departments, separate administrative control. Topologies are totally ad hoc. Wherever you could put a cable, you did. People adding and removing switches or devices without any particular protocol or procedure or necessarily planning. Very low performance and uptime requirements. You know, if you couldn't print, you could complain to your administrator, and eventually the network would come back up and you could print your document. You know, this is sort of the viewpoint. And in that kind of environment, things like RIP and spanning tree were just fine. They enabled this sort of very ad hoc, loosely controlled, decentralized model to do quite well. But really nothing could be farther from the modern data center than this. And to a certain extent, it's going to look like I snuck onto Igor's computer and stole this presentation here, because it's making a lot of the same points here. If you look at today's data center, highly structured topologies, very regular interconnection patterns between aggregation switches, rack-top switches, distribution layer. Centrally controlled, single administrative entity controlling the entire network, very careful change control and testing. And again, one of Igor's points, all of the addressing of this is stored in a database somewhere. I mean, this whole question of like Mac learning, had a customer come to me and feeling very burned by a problem in their network where a particular server had decided that it would answer ARP requests with one MAC address, but then sources traffic with a different MAC address. And so the network never learned where the first address was, yet all the other servers were sending to it using that address. All of this traffic's flooding the entire network. He says to me, I know where my MAC addresses are. Why does my network need to learn them? And this is a very, very interesting point, I think. And if you look at a lot of these dynamic topology discovery protocols, it's the same kind of pattern. The network is learning on its own things that the data center operation team already knows. And this is in an environment with very demanding performance and uptime requirements, and the sorts of instabilities we've seen from the traditional layer 2-3 control plane. It seems like we should be able to do better. And this is the context in which, here's an example of the topology that some of Arista's customers are building, where you have a certain number, typically 4 to 16 spine switches. These are very high capacity, 10 gigabit Ethernet switches, usually operating at layer 3, interconnected in a fully connected bipartite graph down to a top of rack switching layer. Maybe it has a couple hundred switches in it, where each top of rack switch is responsible for a particular rack, obviously, and each rack is sort of its own little IP subnet using ECMP multipath routing to get to spread load across the spine. And this topology can sustain enormous amounts of east-west bandwidth and also be very resilient to link failure. So it's a very good topology. It's just that it's extremely regular and kind of repetitive. And it would be nice if the network knew this was the topology and could save you from the chore of trying to configure it. Because in a network with 400 switches, probably 2,000 IP subnets, depending on how you do it, most of which are really tiny, 1,600 transit links. I mean, this architecture is just made to order for some kind of central control, automated provisioning, automated administration. And this scenario is doable with today's switches. What if you need a layer 2 design? Try to imagine what this looks like at layer 2. What we'll see is that there's really kind of no good way to do it. There's no standards-based layer 2 multipathing approach available today. Trill is coming at some point. Yet another way of routing, another dynamic discovery protocol for, again, something which is fundamentally already known, at least to the network administrators. It's very doubtful to me whether you really want to be flooding every MAC address to every switch in the unknown DA case or to support broadcast-based protocols. Plus, you're still faced with the basic problem of dynamic topology discovery mechanisms that whenever there is an event, this is another one of Igor's points, I feel like I'm just repeating his points here, that whenever there's a topology event, reconvergence is required, and switches can spend an enormous amount of CPU reconverging, and if they defer that work too long, as Igor was saying, that's going to be quite an interesting disaster for the network operators, and none of this seems like it ought to be necessary. So Which approach do you think is going to scale better? To try to get trill and flooding and so on to really scale to an environment with 2.4 million MAC addresses? Or a central controller? So I think we're at a very interesting crossroads here in our industry. So that was actually all I had. So I will turn some time over to the next gentleman here.